and Blake Woodworth. So to set the stage, right, when we're considering optimization in modern machine learning, what do we see, right? We have models that are based on millions and millions of parameters and use millions and now billions of examples to train them, right? So we've gone from the now relatively small MNIST data set of the past to being replaced by something like ImageNet, or maybe even more recently, the billions of tokens used to train these large language models. And similarly, the shallow neural networks of yore, right, have been replaced by these very deep, very dense networks that have led to a lot of advances recently in machine learning. And as I alluded to, right, now we have these large language models, things like GPT-3 with some 175 billion parameters, and GPT-4 with question mark number of parameters, maybe on the order of 1 trillion, who knows? It's a lot. And it's a lot to handle in various aspects, not least of which is the training of these models, right? And it's kind of come to be that methods like stochastic gradient descent and its variants, adaptive variants, momentum-based variants, etc., have proven critical as workhorses of training in modern machine learning. In contrast, right, if we look sort of beyond these stochastic first-order methods to higher-order methods, that is, methods that rely on derivative information beyond just the first derivative, right? Generally, under various assumptions, particularly in convex settings, it's most evident, right? We can get better oracle complexities, right? As the with sort of more derivative information, right? We should expect to sort of converge faster. But as is usual in life, right? There is a catch here, right? With the additional complexity of having these extra derivatives, right? The methods start to lose in terms of efficiency, right? They're much less efficient compared to first-order methods, in particular stochastic first-order methods. And so maybe trying to find a way to balance these things, right? To move in the direction of these higher order methods while maintaining some semblance of efficiency is something we might want to try to achieve. Now, another facet to these gains and improvements and advances in machine learning is moving in the direction of distributed optimization, right? So because these models are so large and the data sets are depend on so many examples, right? No longer can we do all of our training, say, on a single machine, a single GPU. We need to distribute these parts of the training over many machines, right? So abstractly, right, we can think of having many devices that communicate with one another, and we could consider different topologies, right? Maybe something fully connected for how they can communicate, maybe some sort of star topology, maybe some limited amount of communication. And of course, we can have maybe some machines only speaking with others, but not some others in the group, right? More specifically, we see this in the case of how people really do use 4 or 8 or 16 or 1024 GPUs, sort of working in parallel and communicating occasionally to be able to train these really, really enormous models that depend on so many examples. And these distributed paradigms arise arise in the context of what is known as federated learning, right? So here, right, maybe when taking more of a privacy-centric view, maybe there is some big company like Google or Apple or what have you, right, which wants to do some training on data collected, but might not want to collect the data itself, right? So an alternative take might be to have the training being done on clients' devices, right? So each person maybe has a different smartphone or what have you, and to have the training procedure take place in a distributed fashion, right, over their individual machines, and only send the parameters, right, the sort of what's being learned back to the server, aggregate there, sort of update, continue the procedure, and sort of back and forth the process goes, right? So this has, even in sort of the realm of considering issues of privacy, these paradigms are really useful, right? In all of these settings, however, one of the key bottlenecks that arises is that communicating is expensive, right? So just having all of the devices sort of pause with what they're doing and communicate with one another, so that they may update their own parameters and continue the process is really expensive, and thus we want to try and limit how often we communicate, while also balancing that against the optimization efficiency gains or guarantees that we might typically hope for. So we'll take a look at our method federated stochastic Newton, or FedSN, which is a distributed stochastic Newton method, which improves upon previous first-order methods, and under some assumptions, matches some lower bounds. And again, these are with some asterisks for various or particular parameter regimes and under the appropriate assumptions. We also see empirically that we outperform baselines, particularly when we have limited amounts of communication. And one of the core underlying computational aspects of this work is relying on introducing a stochastic Hessian-vector product oracle, right? So this notion of efficient Hessian-vector products isn't new. It goes back to at least the 90s, if not even earlier. And we will bring that into our setting from a stochastic perspective, and we'll get into the details more carefully in a bit. So first, I want to set the stage for what sort of optimization setup we will be dealing with, right? So generally, right, we can consider some sort of unconstrained stochastic minimization problem, right? So it's over RD. Our function is expressed as an expectation, right, for z's drawn from a distribution. And we can think of these z's as maybe corresponding to example label pairs or what have you, but this is a nice, very general way of expressing a stochastic optimization problem. And of course, one of the first things that you want to ask when trying to both develop methods and furthermore analyze them is to ask, what do we know about this function f? Right? Is it convex, which, as we saw in the previous talk, leads to a lot of advantages, right? There's much more that can be said. Or is it non-convex, in which global optimality guarantees will go out the window in general? And furthermore, what can we say about the curvature or the smoothness of the problem? Is it smooth, right? Does it have some nice curvature properties, or maybe it's non-smooth? So different choices among these can lead to different guarantees and different research paths. In this talk, we're going to focus on the convex setting and smooth setting, right? So convex and smooth will be key to this work, although of course we can maybe for other things consider alternatives here. So again, we have now unconstrained convex as the qualifier here, stochastic minimization problem. And as I mentioned, right, we're going to assume smoothness. More specifically, we say that our function is h smooth if for all x and y, the difference or the norm of the difference of the gradients at x and y is bounded by h times the norm of the difference of x and y. Think of it as just a Lipschitz condition, a Lipschitz continuity condition on the gradient. We'll also make a bounded minimizer assumption, right? This really just kind of means that the solution isn't too far away, and of course you should maybe expect to depend on how far away the solution is from, say, where you start, and maybe where you start could by default be at the origin, right? So we'll parameterize that by capital B. And also, as is typical in understanding stochastic gradient methods, we're going to assume some uniformly bounded gradient variance, right? So we'll let sigma square bound the variance. I should also point out that when dealing in a distributed setting, there are a couple of different considerations. We'll be working in what is known as the homogeneous distributed setting, which means that every machine has access to the same underlying distribution of data. In contrast, there are settings known as the heterogeneous setting, whereby each machine has access to a different underlying distribution of the data. And while we don't consider this, it's certainly garnered much interest. Here are just very non-exhaustive list of papers that have worked in that realm. And certainly we can imagine maybe in the federated learning setting, the importance of handling the case where devices data are generated in general by different distributions, right? I also want to note that we work in the stochastic, or sort of the one-pass or streaming setting. And this is in contrast with the batch or the ERM setting, which considers problems of some finite sum form, right? So we really are going to consider a sort of a purely stochastic minimization problem, where we sort of only get to access, or we'll sort of define some sort of stochastic access to information about the function. It's also important not only to sort of set up what the function looks like and sort of how these distributions are formed, but also what is the format of or the structure of the communication. So we will consider what's known as the intermittent communication setting. Basically, we're going to have M machines sort of working in parallel. And these M machines will get to do k iterations of something. So we'll need to specify what that something is, but we want to imagine sort of k operations that take place. And ideally, sort of for all the machines, those k operations will sort of finish roughly at the same time. So we should expect those operations to be comparable in terms of their efficiency. And after these k iterations, we will sort of communicate, right? The communication will take place. The machines will sort of update their information based on information gained from others. And this process repeats for some R rounds of communication. This results in some k times r total parallel runtime, right? So sort of the total number of operations taking place for any given machine is something like k times r, and of course that itself is taking place over in machines in parallel. Now, in this framework, a natural thing to do would be to draw on what we know works well in a sequential setting, right? So this brings us to one method that fits into this distributed framework known as local SGD. And it's really quite natural, quite simple, although maybe not so simple to analyze, it turns out. But the idea is for each machine, basically, we're going to have every iteration be a single step of stochastic gradient descent, right, of SGD with respect to its local parameters. So if we focus for a minute on machine lowercase m, right, and we have whatever its iterate is on this machine, and again, we're kind of putting on blinders and ignoring the other machines for now, we can sort of sample some z from z naught, rather, from the distribution, take the gradients at z naught for the parameters on this machine, take a step of SGD with some step size eta, update our parameter on machine M, take another step, update to the parameter x at M2, and so on and so forth. We do this for all of the machines in parallel, and so it amounts effectively to M parallel runs of SGD. And after all the machines have finished, they take their final iterates, they communicate to them, they are averaged, sent back to the machines, and this averaged iterate is used as the starting point for the next round. And one kind of nice observation here is that local SGD, or maybe even its accelerated variants, it's a method that's very well suited for optimizing quadratics in particular. And essentially, the reason boils down to because the gradient of the quadratic is linear, there's some sort of exchange in terms of like an expectation that happens in the deeper parts of the analysis. But at a high level, we can just sort of take this type of method, for whatever reason, works really, really well for quadratic minimization problems. So what about going beyond the stochastic first order methods? And again, this brings us back to what I alluded to in the beginning of the talk, right? So a classic method for introducing second order information is known as the Newton method, right? So instead of taking a step sort of purely in the direction of the gradient, we're going to redirect it based on the Hessian information, right? This matrix of second order, as we invert the Hessian, multiply by the gradient, take our step and continue. And under various assumptions, this is known to converge fast. if you're sort of close enough to the minimizer under, again, with the appropriate assumptions, you can converge very, very fast. But even in these sort of deterministic settings, it's going to be expensive to compute the Hessian and invert the Hessian, and only more so in a stochastic setting, right? What is it? How does one, without just sort of some pure oracle access, right? How do you get the full Hessian, and let alone the cost that it would take to invert it? And so what we want to ask, right, is whether there's a better and ideally some parallel way to implement something maybe like this. Note that, again, quite simply, an alternative view of Newton's method is simply to think about each step as being the minimization of some quadratic subproblem, right? So some model, some secondary Taylor expansion model around xt is our function q of x. Again, going back to our observation that local SGD works well for quadratics, here's a particular quadratic, right, sort of defined locally for our function. Can we use local SGD on quadratic subproblems of this form, right? One thing to note is that the gradient of this subproblem is something like the Hessian times some vector plus plus the gradient at xt, right? So if we have some stochastic gradient access, oracle access for our function f, then maybe we could use that to get this part of this gradient of q. But of course, that's not sufficient, right? To sort of fully capture this gradient of q, right? We might need some additional oracle access to get at this Hessian-vector product component, right? Now, that might seem a bit of a complication, right? Because this Hessian is some d by d matrix that should take d squared time to sort of write, and then multiplied by a vector, again, some d squared time. But it turns out that for problems with sufficient structure, that we can actually do this quite a bit more efficiently. I like to point this out in the context of generalized linear models, specifically things like logistic regression, where they can be computed in time basically proportional to the same cost of computing a stochastic gradient. How do we see this? If you take a given sample in one of these generalized linear models, the Hessian is rank 1, so we can just kind of shift the product to an inner product, get a scalar, and then multiply it by a vector. So this is kind of a proof of concept of why this might be possible. But it turns out that this advantage that one can do a Hessian-vector product in linear time, essentially, right, sort of proportional to the cost of computing the stochastic gradient, actually it holds also for neural networks, right? Basically, as long as, essentially, if there's enough sort of structure to the function, we can do this type of operation rather efficiently. So this kind of naturally leads us to consider some additional oracle model, right? So we've already sort of seen something like the standard stochastic gradient oracle, right? This is some oracle that will output some random variable such that it's an unbiased estimator of the true gradient, and we need to have some standard bound invariance. So why not also consider introducing some stochastic analog of a Hessian-vector product oracle, right? So similarly, right, we might want to have some oracle that would give us a random variable that would be an unbiased estimator of the Hessian at some point x times a vector v. So this is analogous to this component. And similarly, we want to have, or we sort of expect to need, some kind of bound on the variance of the estimator. And a technical note, though maybe not so unexpected, is that we have both our rho parameter for the variance, but we also have sort of reasons needs a dependence on the norm of our vector v. So that's one aspect, right? We can try to bring additional oracle access into the model and see where that leads us. But we might also want to consider additional restrictions on the function that are still relevant, or that still provide relevance to things that we might care about, which leads to some notion of quasi-self-concordance, right, or the QST condition. There's been much recent interest, and it's a really nice idea that has led to a lot of follow-up work. But the idea is we have some beta quasi-self-concordance condition, which is kind of like the self-concordance conditions for those who are familiar with that, right? Some relation between a third derivative and a second derivative. But the main difference is we don't have a 3/2 power on this Hessian component on the right-hand side. In a sense, the extra like half power gets shifted in a sense from a local notion of regularity to a more typical Euclidean notion of regularity, right? For those for whom this is maybe less clear, basically we can think of this as some additional regularity condition analogous to or something kind of like smoothness or higher order smoothness, right? That sort of just relates some derivatives in a particular way. Its implications are much clearer. So it turns out that all kinds of nice functions and important functions meet to this condition, such as logistic regression, softmax, regularized LP regression. And not only is it met by problems of interest, but it turns out that this condition, with this condition, we can get fast convergence by minimizing not too many or by solving rather not too many constrained quadratic minimization problems, right? So we have a quadratic constrained to some radius of the variable, right? And it can be shown that this converges fast, right? So taking these pieces and putting them all together, right? The main idea of our method fed_in will be to, at every iteration, right, solve some constrained quadratic minimization problem. And because we saw earlier the advantage of local SGD for these unconstrained problems, right, we need to kind of take one more step and break down this constrained problem into a sequence of not too many unconstrained quadratic problems. It really sort of boils down to a typical, kind of like a truss region method, right? And for each of these unconstrained subproblems, do exactly that. We're going to run local SGD on this subproblem with a single round of communication, right? So that's the kind of the interesting thing. Not only is local SGD well suited to quadratics, but it's well suited to quadratics with any number of rounds of communication. And because we want to communicate as little as possible, we might as well sort of only take a single round, right? Just communicate right at the very end. We will need not only the stochastic gradient, but also this extra Hessian-vector product oracle, but we already sort of saw what that should look like. Putting all of these pieces together brings us to the main theorem of the work. Basically, if our function is convex, smooth, reasonably conditioned, has bounded minimizer, and our algorithm has access to both of these sets of oracles, right? Some stochastic gradient and a stochastic Hessian-vector product oracle. Then we get some kind of complicated bounds with a lot of dependence on parameters that I've defined, but that is maybe not so easy to understand, right? We have some exponentially decaying terms here. We have some noise terms, one with respect to the gradient noise, one with respect to the Hessian-vector product noise. And then this term has no noise dependence, and this kind of feels a little bit like the bias or the sort of the gradient descent term if there were no noise, right? So it looks kind of reasonable, and yet it's still a bit difficult to interpret. So we'll try to simplify things a little bit in comparing with previous methods. So one of the previous best methods is FEDAC, which is like an accelerated variant of federated averaging or local SGD. It's a bit difficult to directly compare because of the different assumption sets, right? They consider some third order smoothness. We consider the QSC condition, right? It's a little bit apples and oranges. So we try to level the playing field by introducing some natural scaling parameter D, the details of which are not so important. Basically, suffice it to say, it's an attempt to, again, level the playing field and make a sort of more direct comparison between these methods. When we sort of introduce and account for this parameter scaling, what we find is that we get a rate for FEDAC that looks like this, and a rate for FEDAC that looks like this, and modulo the difference of the power of D and B in the numerator, right? We have sort of a trade-off in the power of K and R, sort of like K to the third, R to the fourth thirds for FEDAC versus a root KR for fed_n. And sort of if we take one more step, we can see by sort of comparing parameters that when R is upper bounded by root k over dB, that is when the number of rounds of communication is small, right? When we have a limited amount of communication, then our method is able to sort of improve upon the rate of FEDAC. There is also a rough attempt to compare with lower bounds. We have some work that has lower bounds under this QSC condition. The main catch is that there the oracle access is with respect to stochastic gradients rather than stochastic gradients and stochastic Hessian-vector products. So again, it's a little bit difficult to directly compare. Maybe there's some sense in which those can be almost interchangeable. Certainly this happens in the deterministic setting, but those issues aside, right, if we want to try and, as a very, very coarse comparison, get a sense of what happens, in this natural parameter setting, when sort of dB is like a 1, and when we have a limited communication, then we get something that matches the lower bounds. So again, there are many caveats here, the clarification of which would be, again, something very interesting for future work. Empirically, too, we see that our method does quite well. These plots are both for some fixed parallel runtime. So this means that we've sort of fixed parallel runtime t to be 100. That means that 100 steps are being taken place. And the x-axis shows the number of communication rounds. So the rightmost points of both of these plots are when we allow 100 rounds of communication, so we communicate every single step. And not surprisingly, right, the methods tend to do better as we get to communicate more often, right? So all the methods kind of have that tendency to do better. The question is, how do the methods do when we have less communication, right? So the right-handmost points are when we only communicate 5 times, right? So sort of 20 steps in between. And indeed, we see that as the amount of communication decreases, we have sort of an improvement, an improved gap between our plots in sort of pink and red compared to standard baselines, methods like FEDAC, local SGD, and mini-batch SGD. I should note that this is for a more empirically inclined variant, which we call FEDS in light, but the spirit is the same. So to break down the problem into sort of appropriate quadratic subproblems and minimize those. Some open problems. As I mentioned, can we extend the lower bounds results that we have in terms of stochastic gradients to account for stochastic Hessian-vector products? Now, it might not seem such a big deal, right? Because we know in the deterministic setting, Hessian-vector products and gradients are kind of roughly equivalent, or they can sort of be transformed from one to the other. But in a stochastic setting, it's a bit more subtle. So there might be some hope for some interesting results there. And this, of course, would complicate what we have, or complement what we have. Another point that might have arisen in the minds of some, right, is asking whether we can use an accelerated variant, right, something like local ACSA rather than local SGD as the main parallel solver for quadratics. There are some technical issues in the analysis that seem to arise from a naive attempt, but maybe there's something that can be done there. And of course, I'm also interested in considering other notions of acceleration, something like Montero-Schweitzer type acceleration, right? Something on the outside of these methods that use these quadratic subproblems. And of course, we can go the other way around, right? We can ask whether local SGD or FEDAC could be analyzed under this QSC condition, right? That doesn't seem to be fully clear. So in conclusion, right, we've seen in this talk a distributed stochastic Newton type method for optimizing QSC objectives. Our methods, so at the heart of our method is leveraging nice quadratic structure of the subproblem, which can be taken, which can be used by certain parallel methods. We get some improvements both empirically and in terms of convergence guarantees over previous first-order methods, while maintaining a similar computational cost. And again, empirically, we see our improvements most pronounced in the low communication regime. Thank you.
Thank you. Any questions for Brett? Very nice talk. So I have a few questions about the convergence rate. Can you tell us what are the parameters like B and T and K in that slide? Yeah.
Yes. So they have to do with the basically the setup of the problem. So they kind of show up a little bit throughout the talk, right? So here's the sigma in the row. Those have to do with the variance of the oracles. There's the beta for the quasi-self-concordance, right? So again, sort of some structure of the curvature of the problem. And then the other key ones are back. Oh, so in our communication setup, right, we have our M machines, our K iterations sort of between the communication and the R rounds of communication. So this gives us the parallel runtime. So M, K, and R are really parameters of the distributed framework, like the setup. And then the final parameters are from our basic assumption, right? So we're going to have our H is our smoothness, B is the bound on the minimizer, this is the minimizer, and again, we have our sigma as the variance bound for the gradients. I think that covered all of them.
Okay, so more like M is like mini batch, and
yes. I didn't discuss mini-batch SGD, but you certainly could recover a parallel mini-batch SGD from this framework. In particular, right, what you would expect to have is a mini-batch size, like if you were to sort of flip things around from the local SGD view to the mini-batch view, the mini-batch size, the natural choice of the mini-batch size would be M times K. Right? Basically, the idea there would be you've communicated, you have every machine has the same starting iterates. Take a K times, take stochastic gradients from that same iterate. Don't step anywhere, just take them at the same iterates, accumulate them, store them, right? Do that over all M machines, and then communicate all of those, right? So that at the end, sort of when you communicate, you would have a mini batch of size M times K. And that leads to different convergence rates, and it's subtle to compare them, but it is important to compare them.
Okay, so do you have separate complexity bound for like gradient and matrix vector modification? Like
yes. So we don't have a separate lower bound to get a sense of what advantage sort of this can provide over just the stochastic gradient. Certainly, I find it advantageous to use it in the context of sort of quadratic subproblems, right? That's sort of the through line. I should note that again, in a deterministic setting, there's essentially no difference between a gradient, and a deterministic gradient, and a deterministic Hessian-vector product. In the stochastic setting, it's a bit more subtle about whether or not you allow for sampling at like the same point more than once. If you require something that's kind of purely stochastic, you have to always sample somewhere else, it's kind of at the whims of the oracle, then this can lead to a divide between what a stochastic Hessian-vector product and a stochastic gradient oracle can do in some other context, in particular in the context of non-convex optimization for reaching stationary points. So we can talk about that offline if you like to, but there's some very, very interesting subtleties here about the power of these oracles.
Great, thank you.
Any other questions?
Great talk. I was just interested in the part where you had the communication. How do you guys think about like the relation between time? Because let's say you just have like a basic, the first like SVD that's running versus this one. When you have the communication, kind of abstracts away the sense of time from, and in some of them, like you have the X with a T. So how do you guys think about that?
That's an excellent question. So we absolutely do abstract it away, and we just assume that everyone finishes roughly about the same time, and of course the reality won't sort of reflect that. So one can account for time and delays, and this has been done, and sort of is continuing to be done in other works for asking things like, maybe you have one holdout machine that's just taking forever. Do you cut it off at some point? Do you ignore it? What happens if there's some staggering, et cetera, et cetera? And what you can do is sort of try to account for this or parameterize this or introduce parameters that reflect to this and analyze under those settings. So with additional complications that reflect reality and arise in realistic situations, come models that try to model those extra complications. So we don't do that, right? We abstract that away, but there is a lot of work that does try to get into those details in a more formal fashion.
All right, so let's thank Brian. And we'll take a short break until 11.